Hello everyone, I'm Mihai Váradi from the Protein Data Bank in Europe Knowledge Base, and today I would like to talk about this new resource that we are developing, and in particular, how this resource can be used in your research to answer scientific questions. So first I will briefly give an introduction to what PDBe-KB is, so the Protein Data Bank in Europe Knowledge Base, and then I will view a few examples of specific scientific questions that you could answer with the help of this data resource. And in particular, I will talk about a graph database that we are making available so that you could use it as a research tool. I will talk about the graph API, which has more than 80 access points that you could use to programmatically access data from this database. And I will also talk about special views called aggregated views of proteins, where you can get all the structural data available for one particular protein. The motivation behind PDBe-KB is coming from the fact that often having the coordinates of a protein or nucleic acid is not enough to answer specific biological questions. You need to have more information regarding the biological context of these molecules in order to answer these questions. And in fact, there are more than 400 databases and scientific software out there that uses PDB data from the PDB, and derive additional annotations from that. And these annotations are part of the biological context that can help you. So the goal of PDBe-KB is to place macromolecular structural data in their biological context by establishing a community-driven integrated resource for structural annotations. And we hope that this will promote both basic and applied research. There are three main goals in PDBe-KB, and the first is to create data standards so that the data coming from all these different specialist resources are converted to a unified data exchange format, making it easier for the users to use it. Second is to create unified data access mechanisms so that users or researchers can access data in bulk from all the different resources at one platform. And finally, we hope that this will decrease fragmentation of the data. And by this, we mean that right now, researchers have to keep up to date with hundreds of data resources, each with their own data formats, each with their own access mechanisms. And instead of this, we would like to provide a platform where it's easier to get all the data that you need. So briefly, the way this works is that in PDB, we have structures, and then the specialist data resources, they take these structures and they can annotate parts of these structures with their specialist information. So for example, one data resource could tell you which residues are on catalytic sites, or which residues are on interaction interfaces of the protein, or which residues are important in the sense that if you mutate them, then the structure gets destabilized. And the idea is to work together with all these data resources and software developers and integrate the data coming from them, map these annotations on top of structures, and map the structures on top of sequences so that the researchers can get a full view of a protein, not just parts which are covered by specific PDB entries. This is a collaboration, an open collaboration, and to date we have 26 collaborating data resources from across the globe. And what's important in this for the users is that we want to provide a one-stop shop, basically a platform that you can come to and get different types of annotations, all derived from structures. The infrastructure of PDBe-KB looks something like this. And today I will talk about the three main components. So the graph database, the RESTful API, and the PDBe-KB pages or aggregated views. So first, the graph database. In the graph database, we are combining the core PDB data with the annotations coming from all the partner resources in a highly interconnected graph database, which is implemented in Neo4j. So this database consists of nodes and edges, like any graph. And in the case of this database, we have almost 1 billion nodes and 4 billion edges connecting these nodes. The data is around 0.5 terabyte in size. And provided you have the storage, you can just grab this database, you can spin up an instance. Actually, we are providing tutorials for how to do that. You can go to this link, you can grab the complete archive, and then you can write sophisticated queries that can give you a very specific data set for your research. So the way it works, this is a quite simplified view, but basically it conveys the idea that all the PDB entries have one main node, and then each molecules in that PDB entry are represented as other nodes, and those nodes have residues. And for each residue in the PDB, we are directly mapping to UniProt and the UniProt entry, as well as if that particular PDB residue is interacting with a small molecule, then this is encoded in the graph. And if there are any additional functional annotations, so for example, is this residue on a catalytic binding site, or is it predicted to be intrinsically disordered? Those are also encoded in the graph. And I will show 3 examples that we received from actual users of this graph database. So people who approached us and said that these are the questions I have for my research. So the first is, can I find all the small molecules in the database that have the same scaffold and that interact with the same binding sites? And this is something you can quite easily do in this graph database. And in fact, you can add additional information such as, are these binding sites catalytic sites, or the small molecules, are they drug-like, are they cofactor-like, reactants? How conserved are these shared binding sites? And much more than that, actually. So if you were to look at the graph, this is what you would see. You have one isoleucine here, which is actually a residue from UniProt. And you can see that this particular residue is represented in 2 PDB residues. So basically there are 2 PDB entries that have this isoleucine. And in the graph, you can see that actually both of them have connections to a small molecule, different small molecule, and these 2 happen to be antibiotics. And if you look at those small molecules, you can see that actually they are similar, which is based on several criteria. One of them that you can filter for is that they have the same scaffold. So this is already visible if you just look at the graph database. But if you actually look at the examples, you can see that indeed, these 2 antibiotics, they have the same scaffold. And if you were to visit one of these aggregated pages, aggregated views that I will talk about later, you could go to the ligands section and you could see which residues of the protein are interacting with which small molecule. So here on the x-axis, you can see the residues of the protein. And these blue boxes, they represent the residues which are interacting with a particular small molecule. And so you can see that basically there is only one residue difference in interaction between these 2 small molecules. Another example that we received was, can I find all the macromolecular interaction interfaces where the residues are both highly conserved, but also predicted to be structurally disordered or flexible? And again, yes, this is doable with the database. And in fact, you can add information like what domains are mapped to these residues, or do these residues fall into a specific type of secondary structure element? And if you were to look at the actual graph, the way it looks like is it will come up with the groups of amino acids. And on one of the edges, you would find the value for the conservation, for the sequence conservation. You would also find on their actual node if they are predicted to be disordered or not. So this information is coming from a resource called MobiDB. And also you could see that actually it interacts with another protein. So it is on interaction interface. This interaction data is coming from PISA. And the third question that I would like to show today is about variants. So is it possible to get all the residue pairs from the complete PDB archive, where there is a residue and in one structure it's the wild type and in another structure it's some kind of variant, but the same exact position of the protein? And this is also quite straightforward actually to do in the graph. And you can enhance this data set with information on are these residues involved in interaction interfaces? Are they interacting with small molecules? And in fact, if you are interested, you can dig down to the atomic level details of small molecule interactions. Are these residues conserved? Are they buried, accessible? How accessible they are in terms of angstrom squared? And are these flexible? And so on. Actually, there are much more in there. If you were to look at a specific example, you could see this. For example, we have a glutamine here, and this is the uniprot residue. You can see that all these blue circles, those are from different PDBs where you actually have this uniprot residue. And you can see that in the majority of the cases, this is a glutamine, but there are a few cases where it's not. And one of the cases is it's an aspartic acid. And I just zoomed on this particular residue because then you can see what information we actually have for that particular node. And so, for example, here we have information on backbone flexibility, for example, or is it an early folding residue? Or I think this is about the interaction interface size, if it has any. Then we have domain annotations from Interpro, Scope, CathB, Cath, and also we are directly mapping this residue to ensemble as well. Additionally, it turns out that this particular aspartic acid is involved in interaction with a small molecule as well. These are a few examples of what you can do with the graph. And in fact, if you are interested in more, you can just go to this location. It's a Google Drive folder where you can find more materials. You can find the actual queries that you could write and would return these results for you. But there are much more in there as well. We also have a tutorial that you could visit and learn how to retrieve the database, how to set it up. Actually, it's quite straightforward to set this up, and how to write queries. You can also look at the database schema, which actually tells you what exactly we have in the graph and what nodes and what edges are there. And like I said, you can download the complete database, which is refreshed every week. So every week it's up to date. Next, I would like to talk about the REST API that allows access to all the data that we have in the graph database. And so if you don't want to interact with the graph database itself, you could look at these more than 80 endpoints and try to get the data programmatically this way. So these are endpoints that return the data in JSON format. And a few examples of what you could do with this API. So suppose you have a protein of interest with a specific uniprot ID or accession ID, and you want to get all the PDB entries which are at least 90% sequence identical to your protein of interest. Then you can go to this URL and this gives you a JSON format data. Or suppose you are interested in what complexes can you see in the PDB where your protein of interest is a member of. So for that, there's this URL. If you go there, you can get the data. Or this is something that comes up quite often. Suppose there is a long protein and there are many different segments which are covered by different PDB entries. And suppose there is a well-studied segment which has hundreds of PDB entries. So how do you choose one representative out of hundreds? And for this, there is a particular API endpoint. And the criteria for choosing a representative structure for a specific segment is by experimental method, resolution, as well as coverage and overall data quality. So moving on to the last part of this webinar, I will talk about these PDBe-KB pages called aggregated views. And I will put this in the context of the coronavirus. because we have these pages for each of the coronavirus proteins as well. So the reasoning behind these aggregated views is that traditionally PDB entry pages display information for one specific PDB, logically enough. But this means that if you're interested in a full-length protein, then often you have to visit many, many different pages and get the data from each of these places and compile it yourself. So instead, we were thinking that maybe we could create a page that already aggregates all the structural data for a protein, not from just one PDB entry, but from all the PDB entries related to that particular protein. And so we are collecting all the data we have and displaying it on these pages. This includes everything from domain annotations to biophysical parameters. This is the example of one of the coronavirus proteins. This is a polyprotein. And as you can see, there are already 121 different PDB entries for this particular protein, and also 121 small molecules, as well as 8 different similar proteins. So one thing I would like to highlight here is this panel on the right. And what you can see here is that the polyprotein is quite long, and different segments of it are covered by different PDBs. So for example, this blue box, this means that for that particular segment of the protein, we have a PDB entry, which happens to be 6WEN. But if you are interested in a different part of that protein, you can use this panel to navigate between the different sections. And you can see that, okay, for that region, the representative PDB would be 6M71. If you click on any of these images, then you get to an interactive 3D viewer called Monstar. You can also download all the coordinates for different options. So for example, you can, in this case, if you want to get all those PDB entries where there are small molecules, then you can just click here and you will get 115 different PDB entries. Right beneath this section, we have structures and domains. So here you get an overview of all the PDBs that are covering the different regions of the protein sequence. And you can compare that information with domain mappings and secondary structure information. We have a specific section for small molecules. And on one hand, there is a gallery where you can download all those PDB entries where you have one particular small molecule present. And on the other hand, we are also showing here annotations if we have any. So for example, if we know that this is a cofactor-like molecule, we are placing it there. And underneath this gallery, we have a sequence feature viewer called ProtVista. And you can use this to actually look at the residues which are interacting with these small molecules. So one of the features I really like in this is that if you collapse the track for the ligand binding sites, then you can see patterns. You can see which are the residues in the protein that are consistently interacting with different small molecules. And if you expand it, then you see that, okay, for this particular small molecule, these are the residues which are involved in interaction. But if you collapse it, then you can see that actually these two residues, they are always interacting, well, except for this particular instance. We have the similar setting or setup for macromolecular interactions. Again, we have a gallery, and if this interaction partner has a UniProt accession, then you can actually go to its own aggregated view page. And also, again, we are showing which residues are involved in interactions. So basically, we are showing you the interaction interface. And finally, we have a section for similar proteins. And in the case of coronavirus, what we can show here is that, are there any other UniProt accessions? So this is the UniProt accession of the coronavirus protein. Are there any other UniProt accessions which have PDBs mapped to them that are at least 90% identical to any PDBs mapped to this one? And it shows you where that PDB is mapped to. So for example, this first row, this says that this particular uniprot has a PDB structure there, which is 90% identical to a PDB structure mapped to the same segment of your protein of interest. One thing I would like to highlight is that you can not only download the coordinates, like you've seen previously, but you can also get all the other data that we are showing. So all the annotations, all the ranges, all the text, everything in both CSV and JSON format for all the different sections. So you can grab the data and then you can perform any kind of analysis. So the main highlights of these aggregated views, you can get an overview of all the structural data there for one particular protein keyed on uniprot accession. You can view any of the related PDB structures in a 3D molecular viewer. You can download the coordinates in updated MMSIF file format, and you can download all the annotations that we display in both CSV and JSON formats. So the last thing I would like to show is this slide. If you are interested in trying out the graph database or the API or look at the pages, then these are URLs that would be very useful for you. And like I said, all the materials that can help you with this are available in the Google Drive folder here. So thank you for your attention.